I'm going to do another example of delta G naught and temperature. We can manipulate the driving force with temperature, and sometimes we can make it go spontaneous, and sometimes not. Let's take a look at this reaction, calcium carbonate. Calcium carbonate is found in limestone. In fact, limestone is made up of calcium carbonate. Let's look at limestone decomposing into calcium oxide and CO2 gas. Does this reaction happen spontaneously? Does limestone, if you have limestone tiles or limestone? No, it doesn't. And so we already know that this is going to be delta G naught is greater than 0. But if we look at this here, what do you think? Is it endothermic or exothermic in the forward direction? It's endothermic. So the energy is going up. And also the entropy is going up. And so if the entropy is going up, then this is what we call non-spontaneous at low temperature, but spontaneous at high temperature. So this one we might be able to make go spontaneous if we have the appropriate temperature. All right, so we need to calculate delta G naught. This is delta G naught at 298 Kelvin. It's non-spontaneous, but maybe at a different temperature it would be spontaneous. If we're looking at the temperature, we're not going to calculate delta G naught at 298. We could do that using the delta G formation. Instead, we're going to look, is there some temperature? So delta G naught at temperature T, well, this is going to equal delta H naught at temperature T minus T delta S naught at temperature T. Unfortunately, we don't know what the temperature is, and so we're going to make an assumption. We're going to assume that this is going to be about equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. For the most part, this is a reasonable assumption, unless something changes dramatically. And so let's go ahead and calculate our delta H naught at 298 Kelvin. So delta H naught at 298 Kelvin, you can just look that up. So the easiest way of doing that would be the delta H formation of the products minus the delta H formation of the reactants. And so the first product here is calcium oxide. Look at the delta H formation, which would be the first column, minus 635.1 kilojoules per mole. The calcium oxide is minus 635.1 kilojoules. We have 1 mole, so it's just that many kilojoules. CO2, carbon dioxide, delta H formation is minus 393.5 kilojoules per mole. So this is going to be plus a minus 393.5 kilojoules. So again, we just have 1 mole of stuff. And so this is the sum of the products minus the sum of the reactants. So let's figure out the reactants. Well, there's only one reactant. It's calcium carbonate. If we go to calcium carbonate at the top, it's minus 1207. So it's going to be a minus 1207 kilojoules per mole. We only have 1 mole, so it's going to be kilojoules here. All right, so let me erase this here. And so what does that come out to here? Go ahead and calculate that. So we got 635.1 plus 393.5 minus 178.4. So it's going to be plus 178.4. Well, subscript the 4 to indicate that 4 is not significant as far as sig rules go. And so if we look at our delta G equation, delta G at temperature T under standard conditions is going to be plus 178.4 kilojoules for our delta H term minus T. Okay, then we'll get our delta S term. And so if we calculate our delta S at 298 Kelvin, and again, we're making the assumption that at 298 is going to be the same as at temperature T, so it's not exactly the same, so we can just do that to the equal sign. And so delta S naught at 290 would be the absolute entropy of the products. And the first product is calcium oxide. Let's find that here. That would be the first one, 39.75. The entropy of calcium oxide is 39.75 joules per Kelvin mole. 1 mole, so it would just be joules per Kelvin. Plus the entropy of CO2. The entropy of CO2 is 213.7 joules per Kelvin mole. Again, 1 mole. There's a solid and a gas. And then over here we have a solid. Did I talk about Trouton's law? I forgot to talk about Trouton's law. Maybe I should make brief mention of Trouton's law because, I shouldn't call it Trouton's law. It's not a law. I should call it Trouton's rule. Because law, law is some kind of pattern that. Do you remember the scientific method? The scientific method. What were the steps in the scientific method? Observation. And then what? Yeah, this was from day one, so hopefully you would have read it at least 20 times by now. Maybe 10 to 20 times by now. And so you start off with observation, and then you look for what? Patterns. And those patterns, if they fit some kind of mathematical format of mathematics, we call it law. Laws are typically what type of equation? Empirical. Oh, good, Joanna, you got it. Empirical equations that fit the data. Well, a rule, what do you think about a rule? Is a rule better than a law, or a law better than a rule? A law would be. A law would have fewer exceptions. Think of the solubility rules. Are those laws? No, those are rules. All right, so we have Trouton's rule, which I didn't talk about. Trouton's rule just says this. If you take substance A, which is a liquid, and you vaporize it to substance A, which is a gas, so you're just vaporizing it, and what is the change in entropy? Well, I would say this as just being, if I were to do the same thing as Trouton's, I'd call it Chabau's rule. Chabau's rule says that a gas is about how many joules per Kelvin entropy? About. So sorry for this aside. I realize I forgot to talk about this. How many joules? Well, this is the entropy final, entropy of the products minus entropy of the reactants. Entropy of the product is about what? Gases are about? Yeah, so 200. Liquids are about? Oh, 50 is getting low. 50 is getting into solids. I mean, in fact, I think this is kind of low. 39.75. The entropy of calcium oxide is only 40. It's kind of low. It's pretty ordered compared to calcium carbonate. Calcium carbonate is on the, actually, what is the entropy of calcium carbonate? Calcium carbonate has an entropy of 92.9, which is a little on the high side for a solid, It's on the high side because of the carbonates. But we would say that, gases 200, liquids 100. So Chabau's rule would just say delta S of vaporization, this is vaporization, is about 100. 200 minus 100 is about 100 joules per Kelvin mole, or mole Kelvin, doesn't matter. Well, it turns out that, Trouton was trying to be more precise. You know what Trouton said? Trouton said that the delta S of vaporization is equal to
87 or 88. Actually, I can't remember because I don't pay much attention to Troughton's rule, but I need to mention it because I think the homework asks you to do it, and some people will ask you to do it. So Troughton's, what Troughton said. Troughton said that delta S of vaporization is 87.
So I just said, hey, you know, it's about 100. What does Troughton say? No, it's about 87. 87 joules per Kelvin. Wow, that's precise.
You know, I would hesitate in going that precise because there's some variation, right? How good do you think Troughton's rule is? Should we start calling it Troughton's law? Delta S of vaporization is 87? Oh, come on, 87? Are you serious? You know, can you get that precise? Well, if you're benzene, then it's 87.1. If you're, this is benzene 668. If you're this, which is called octane, C8H18, you're 86.2. Well, 86.2, 87.1, we'll just call it 87. Is that pretty good? We got two examples there. But you know, if you're water, you're at 118. If you're water and you're 118, is that pretty good? Troughton's rule? No, Troughton's rule fails for water, right? Fails for a lot of other things. But you know, it works okay for hydrocarbons. If you're dealing with hydrocarbons like C6H6 or C8H18 and other hydrocarbons, then it's decent. You know, the spread isn't so huge. But once you start adding like alcohols or carboxylic acids or water, forget it. It's not going to work. Okay? And so Troughton's rule is kind of restricted for a certain type of liquid. And so this is why it's covered in the book. Okay? But once you introduce stronger intermolecular forces, like in water, hydrogen bonding interactions, which are pretty strong, then Troughton's rule says that delta S of vaporization is going to be greater than 87. But well, anyway, these are kind of, what kind of things we would expect for entropies. You know, these look reasonable. You know, calcium oxide, CO2, etc. And so, since I forgot to talk about this when we were talking about delta S's, just insert it there. But here we're going to calculate the delta S. I can guess, I can guess the delta S here. What do you guess the delta S is? If I were to have to guess the delta S, I'd say, 0 to 100, right? 200, 0 to 100. And so these would kind of cancel out. And I'd say it's going to be close to 200. You know, that's kind of like Troughton's rule, but applied to more things. What it does is it gives you a ballpark number in your head, so you know. Troughton's rule, they try to use it for calculations because it's a pattern that they see. All right, now let's go for this. Let's see how close we are. I think we're going to be off, of course, but 39 points because the entropy of the solids are kind of different. And 39.75 plus 213.7 minus 92.9, 160.55. And so was our guess terrible? Our guess wasn't terrible. You know, we guessed about, what, 200? And came out to 160, so not terrible. But anyway, we're going to get these in the same units. And so this is going to be 0.1605. I'm going to subscript the 5. Just carry some extra kilojoules per Kelvin. And so over here, this is going to be temperature times 0.1605 kilojoules per Kelvin.
Now, at 298 Kelvin, let's say at 298, is this spontaneous or not spontaneous? So we'll just go ahead and calculate it. So just throw in 298 in there. And we end up with this. At 298, so delta G at 298 under standard conditions is equal to plus 178.4 kilojoules minus 47.8. I'll just carry one extra digit, 8 kilojoules. And so do you see this unfavorable enthalpy or energy is not quite canceled out by the entropy. And so this is still going to come out positive. It comes out to plus 130. It comes out to plus 130.5 kilojoules. On a plus 130.5, what would you call that? Would you call that mildly non-spontaneous? Or you know, moderately or significantly? Well, yeah, it's pretty. This is a pretty significant barrier. This is a highly non-spontaneous. You can say that. I mean, it's a pretty big barrier to overcome, and so this is non-spontaneous. But this is a special case where the entropy is favorable. When the entropy is favorable, then what we can do is just bump up the temperature. We keep increasing the temperature, making this number bigger. Bigger and bigger. We want this number to go to minus 178.4. So if we go from 178.4 to minus 178.4, we can cancel out the unfavorable energy with the entropy. So let's do that. We just got to figure out what temperature will make this term a minus 178.4. And so what we'll do is we'll just try it at some temperature T. And so we'll do delta G naught at T, which is going to equal plus 178.4 kilojoules. We'll get minus T times 0.11160, actually, 16055 kilojoules per Kelvin. And what we want to happen here is we want this one to cancel out this one so that it ends up equaling 0. And that way, we convert this from being non-spontaneous to spontaneous, because we just have to push the temperature a little higher to get it negative. And so what is that temperature cutoff there? Again, this is going to be approximate because the delta H and the delta S. So T is going to equal 178.4 kilojoules divided by 0.16055 kilojoules per Kelvin. And that gives us a temperature of 1111. I'm allowed 3 sig dates, 11.1 Kelvin. Minus 273. Let's do minus 273. 838 degrees C. 838 degrees C, 0.1 degrees C. And so what this means here is that at room temperature, calcium carbonate is not going to decompose, but if we increase the temperature to 838 or above, it should start to decompose. So here we go. Calcium carbonate goes to calcium oxide solid plus CO2 gas. And temperature required is 838 degrees C. Temperature greater than 838 degrees C will go spontaneous. I saw a TV show on this on the Discovery Channel. So watching the Discovery Channel, they were talking about ancient Rome and how the ancient Romans had a pretty steady food supply, so they could do some chemistry experiments. And one of the chemistry reactions that they did was this one. they had some ancient kilns in which they could get the temperature pretty hot with coals to 838, so they needed decent coals to get to that temperature. And then they could decompose the calcium carbonate. It would form calcium oxide. Calcium oxide is a critical ingredient in concrete. You need this is called lime. And so they were able to manufacture concrete and build some amazing structures with that. But, you know, that's assuming you can get to this temperature. Sometimes, you know, sometimes the temperature is not feasible. Sometimes you do a reaction like this and the temperature comes out to like 40,000 Kelvin. Do you think the ancient Romans could come up with 40,000 Kelvin? With some ancient kiln? What about modern day? If we use a modern day kiln, are we going to get to 40,000 Kelvin? What do you think? 40,000 Kelvin would be, what, how many degrees C? Maybe like 38,000 degrees C, you know, 38,000, 39,000, well, actually, no, 39,700 degrees C. We're going to get that temperature easily? You know, at temperatures like that, it vaporizes. I mean, I guess if you shot it into the sun, maybe you do that. Or if you would have to isolate it because any kind of container that you would use would vaporize. They're trying to get to extreme temperatures, you know, trying to do fusion reactions, but there's no container there. They just isolate it in space using electric and magnetic fields. And so there are some temperatures, even though you can calculate it, they just aren't feasible. Like something like 40,000 Kelvin wouldn't be feasible. And so maybe it's not going to be spontaneous. Or there are other temperatures. Some reactions are, you know, the opposite scenario where when you lower the temperature, they become more spontaneous. And so sometimes you'll do a calculation and you'll calculate, oh, at minus 400 Kelvin, it should go spontaneous. Well, is minus 400 Kelvin a feasible temperature? You know, no, it's impossible. That temperature doesn't exist. So, you know, even though the math will calculate some ridiculous temperature, and that's the correct answer because the math is correct, it's impossible to attain. This one is feasible to attain, but sometimes they aren't. And so what we can do is we can look for other things that can help the reaction go. Some of the other things might be to couple the reaction. And so if we can couple this reaction with something else, maybe we don't have to heat it as hot, you know? And so, fortunately, the Romans had the coal they could do this with, but you know, maybe it's some other cultures they couldn't get it this hot. And so, if they can't get it this hot, then how would they do that? Well, maybe they could do this because this is what they want. This is the product. They don't want to touch this, but maybe with the CO2 you could couple it. And so, to bring the temperature down, because this is going to be a high temperature nonetheless. I mean, to get that, it's going to cost a lot of energy. So we might try to bring it down by seeing if we could react the CO2 in a favorable, you know, this is delta G is positive, but if we can come up with a reaction where CO2 reacts with something else, right, we could get delta G a negative, and even though it might not be enough to overcome, because it's a lot to overcome, plus 170 kilojoules, it's a lot to overcome. But even if we can drop it down a little so it's less positive, then the temperature is not going to be as high. You know? And so, you know, this is kind of high temperature, you know, but we might try other tactics, to make this reaction more spontaneous. And the other tactic that we tried was coupled reactions. So let's do this as an aside here in this problem. Okay, so what we try to do is we try to figure out something that reacts with CO2 quite favorably. Can you think of something that reacts with CO2 quite favorable? So you think things like metathesis. Well, CO2 is not an ion, right? You think about redox. CO2 is an oxidizer, but it's extremely weak oxidizer. You think about acid-base, but CO2 is a what? What kind of acid is it?
It's not your typical acid. CO2 is what we call a Bronsted acid. No, it's not a Bronsted. Bronsted acids are proton donors. So what other types of acids do we have? Lewis. It's a Lewis acid. In fact, this is what they do on the space station. On the space station, they don't want CO2 in the air, air that the astronauts breathe, because if the CO2 concentration goes higher and higher, it affects your blood pH. It makes your blood pH go lower and lower, which could be toxic. And so CO2 is a toxic gas. And so they scrub the CO2 using hydroxides. So, you know, they don't use sodium, they use lithium hydroxide. Lithium hydroxide is lower in terms of formula weight or molecular weight. But this is a Lewis acid-base reaction. Lewis acid-base reactions are more complex. So this is why I don't really talk too much about them. But this would form, we need two of these. We're going to form sodium carbonate and water. Sodium carbonate will eventually dissolve. There's enough liquid water for it. So I'm not going to put the state there. But you know, this is favorable. The delta G is negative. The delta G here is positive. And so is it negative enough to cancel that out? No. But it's negative enough to lower that, so we don't have to maybe go as high of temperature maybe. So those are approaches, but are there any other approaches other than coupled reactions? Yeah, there are other approaches that we can take. And so other approaches here. I have to step out. The other approaches are to go non-standard conditions. That is, we can increase or decrease the concentration. Because standard concentration is 1 molar. Or we can increase or decrease the pressure. So over here, you know, for example, if we decrease the pressure of CO2, that could help us in this reaction. It could make it easier. And so we could try non-standard conditions. In order to do non-standard conditions, we have to know two things. We have to know Q and K. Q is called the reaction quotient. We'll talk about that. K is called the equilibrium constant. And so we need to know Q and K and delta G. And so let's, or delta G naught, delta G naught, whichever. All right, so what I'm going to do, Q and K are talked about in chapter 13, but really what I'm going to do is I'm going to jump to chapter 15 right now because it's easier to talk in chapter 15 perspective. First off, we're going to look at this reaction here. I'm not going to go right in the order that they're doing. But we're looking at this reaction. This is chapter 15, section 1. And so we have copper 2 plus here, AQ, plus tin 2 plus AQ. And in this reaction, we're going to form copper plus 2 of those and a tin 4, and like this. The first thing we might go for is let's go ahead and just calculate under standard conditions what is the delta G naught. And so under standard conditions, what would the delta G naught be? And so we'd go over here, A, T. So we need copper and tin. Let's go through, find copper. Here's copper. And so take a look at the data table there. And, go ahead and
start the calculation here. Well, I see, you know, what's the easiest way of figuring out what delta G is? What's the easiest way of figuring out delta G? Is it by calculating delta H and delta S? No, it's by using delta G's of formation. It's not as versatile because when we use delta G's of formation, that restricts us to one temperature. And we can't change that temperature. And so we'll just do it though, because delta G of formation of Ce2 plus is 65.49. That's okay, but we got to do the products first. The products minus the reactants. And so when we look at the delta G of formation of the products here, I need copper plus. Do you see copper plus? No, I don't see copper plus. If copper plus is missing here, then I might as well just give up, because there's no copper plus here. But would you give up that easily? No. But you know, we're already in the biggest table, appendix D, and there's still no copper plus. So I guess I could do a Google search. I actually did a Google search a while back. I don't know if you remember, but I couldn't find it then either. And so maybe I should have given up at that time. But we aren't, because what we want to do is we want to figure out as many different ways of doing things as possible. And so even though I don't have the number, and I'm not going to get a number, maybe I can say something. You know, is this spontaneous or not spontaneous? Because that's what delta G is telling us. Delta G is telling us, is there a driving force or no driving force? So is there some other way I might be able to figure out if there's a driving force for this? At least figure out if delta G is negative or positive. Is there a way to do that? Yeah, actually there is. It wasn't covered in any of the chapters, but it's kind of Chem 1A style thing that we did earlier. And that is, what type of reaction is this? A redox reaction. So how do we figure out if there's a driving force for redox? Strong to weak. And so we don't use this. We don't use this data table. We're going to use what was the name of that data table? Does anybody know the name of that data table? Obviously the name of the data table is written at the top of the table, but does anybody, because I never called it by its proper name, can anybody see what the proper name of that data table that we need is? It isn't this one. It isn't this one. It's down here, I think it was. Oh, here it is. I called this, what did I call this data table? I just called it the redox chart, you know, the strength chart, whatever, but you know its official name? Its official name is not really this. Its official name is called standard, because everything's under standard conditions. It's called standard reduction potentials. This is the standard reduction potential chart. And these are the standard reduction potentials over here. That chart is actually not the standard reduction. That chart's called the standard oxidation potential chart because they put the reducer on the left. Over here, they put the oxidizer on the left. And so oxidizers take electrons and are reduced in the process. So as we go left to right, that's called a reduction reaction. And so this is why it's called the standard reduction potential. Standard reduction potentials are common now. One time it used to be standard oxidation potentials, but no longer. They're the same chart essentially. Both of them have fluorine and lithium. But anyway, we look for stronger to weaker. So let's look for copper 2 and copper 1. Actually, since we're going from reactants to products, we'll just look for copper 2 for right now and copper 1. So let's see. I don't see it here on the first page of this. Oh, here. Here's copper 2, but I can't use this. Why? I don't have any iodine here.
here's copper 1. Can I use this copper 1 here? I can't use this because this is the copper 1 copper conjugate pair. Do I have copper 1 and copper metal? No. And so I cannot use this one. Can I use this one? There's I found copper 2. I can't use this one either. No copper 2 here. Sometimes if I can't find the oxidizer, I'll look for the reducer. Oh, actually, I don't know. I don't know if those are oxidizer reducers. Maybe I'm looking on the wrong side. Let's take a look. What's the oxidizer here? Copper 2 or tin 2? Just look at the both can be oxidizers, right? But in this reaction, what is copper 2 acting as? An oxidizer or reducer? Oxide is taking an electron, it's taking one electron, so this is my oxidizer. Tin 2, is that oxidizer or reducer? How about in the reverse? What's the oxidizer and reducer in the reverse direction here? Copper is the reducer. And tin 4 is the And so I need this conjugate pair, the copper 2, copper 1 conjugate pair, but I haven't come across that yet. And copper 2 is the oxidizer, so copper 2 should be on this chart. I see copper 2 up there. I see copper 2 here, but this is a copper 2 copper conjugate pair. I don't want that. And so I keep going down. Oh, what do I see here? I see the copper 2, copper 1. So this is the one I want. So this is my oxidizer. And then I look for, what's my other oxidizer? Tin 4. Which one's stronger? Copper 2 or tin 4? Copper 2. And so what that means is we're going from stronger to weaker. Stronger to weaker. That means the reducing agents must follow the same pattern. So if we take a look at the reducing agent, lithium's way down here at the bottom. So tin 2 is stronger than copper 1. This is stronger. So we're going from stronger to weaker. We say there's a driving force. If there's a driving force, we say it's spontaneous. And then we say that delta G naught is less than 0. Delta G naught is less than 0. And so this allows us to do our Chem 1A stoichiometry. But I'm going to set it up in the Chem 1B style, And so let's try a little stoichiometry because this reaction should go. So we're going to try some stoichiometry. And so the way we set up Chem 1B stoichiometry is like this. We set it up as a table rather than doing dimensional analysis. And so the table is called an ICE table, ICE. And I'm just going to pick some, this is just an example. Let's say I start off with 1.00 moles of copper 2 and 1.00 moles of tin 2. And so this is just your standard stoichiometry problem. You have some amount of reagent 1 and some amount of reagent 2, and then there's no product here. So nothing's reacted yet. And so this is what we call the initial of what we're given. And then what's going to happen? Well, there's a driving force, right? The driving force, so we should get reaction. Now, when we get reaction, we look, what is the limiting reagent here? Copper 2 is the limiting reagent. Now, if we have 1 mole of tin, we need 2 moles of copper, so it's the limiting reagent.
what happens to the limiting reagent in a stoichiometry problem? The limiting reagent is completely consumed, right? And so that means the change here is going to be minus 1.00 moles. We're going to lose all of it. So the end of the reaction we often call equilibrium. At the equilibrium phase, equilibrium means no more change. Everything is reached stable end. Well, anyway, so we end up with 0 moles of limiting reagent. That means we're going to have excess reagent left over. And so how much excess reagent do we have left over? Yeah, we're going to have 0.50 moles of excess reagent left over. The reason is because we're going to consume 0.50 moles of our original. Sometimes this is hard to see, but actually it's very easy to see because the way I visualize this is like this. And, the way I visualize it is by looking, at like tin here. Tin, we call this minus Y here. If tin is minus Y, then copper is minus 2Y. And so, and we do that based on the coefficients here because the coefficients are 2 to 1. And so this is how I look at the change. And so if 2y is 1.00, then y must be half of 1.00, which is 0.5. And so if I lose that, then I gain that. And so this makes this easy. This is going to be plus 2y, right? Plus 2y because of the coefficients. It's a 2 to 1, 2 to 1 ratio. And so what is plus 2y? Well, plus 2y is plus 1.00. And so I'm going to gain plus 1.00 moles here. So at the end of this reaction, I'm going to be left over with 1.00 moles product. And how much tin 4 do I form? Well, tin 4 is plus y because the coefficient's 1. So that would be plus 0.50 moles, which means I'm going to end up with 0.50 moles of tin 4 at the end. Does that make sense? And so this is what we predict based on Chem 1A stoichiometry. And that's what in chemists we like to predict things. So we predict based on Chem 1A stoichiometry. And so what we'll do is we go into the lab and do this. We go into the lab and do this. And this is what we predict. Is our final, well, what's observed experimentally is this. For the copper 2+, we end up with the copper 2+, we don't end up at 0. We end up at 0.36. 0.36 moles. Let me just write it down. And so this is n predicted. This is the n observed. The end observed is not 0 moles. The end observed is 0.37 moles. So what we can do is we can do a quick mental calculation. A quick mental calculation means that we didn't consume 100% of it. How much did we consume? If we started off with 1.00 and we end up with 0.37, let's do this. We'll move the decimal 2 over. So we start off with 100, we end up with 37. If we start off at 100 and end up at 37, then we consume 63%, not 100%. And we're left over with 37% that won't react because this is hit equilibrium. There's no more change once you hit equilibrium. No more macroscopic change.
And so that's off. And then the tin 2, the tin 2, actually, maybe I should redo this here. So we see we've lost 63%. We lost 63% moles. And so if we have 1.00 moles of tin, at the end we're left with actually 0.68. And so how much did we lose? Well, we started off with 100. We end up at 68, so that means we lost 32. Lost 32% of the excess reagent. But, when we're thinking about reactions, we often like to think in terms of percent reaction. And so here there's a difference. Here 63% reaction, here 32% reaction. Which is it? Is it 63% or 32% reaction? Well, the percent reaction is always based on the excess reagent or always based on the limiting reagent? It's always based on the limiting reagent. And so what we'd say here is we had 63% reaction. We expected 100% reaction. Because if we look at the limiting reagent over here, 100% of it should have reacted. If we looked at the excess reagent, we predicted 50% of it reacted. And so we're going to base it on the limiting reagent, which is over here. And so we only got 63% reaction. And so we lost 32% of our tin. We started off with 0 moles of copper plus, but we end up with experimentally 0.64. And then we started off with 0 moles of tin 4, and we end up with 0.32. Now, Chem 1A stoichiometry failed in one sense. It failed in the sense that we didn't end up where we thought we were going to end up. But it's not a complete failure because Chem 1A stoichiometry has to hold. That is, the mole ratios have to hold up. We can neither create nor destroy atoms. And so what we say is if this is minus 2y and this is minus y, then this would be plus 2y and this would be plus y. And so what is y? Y is 0.32. 2y is not 32, not 0.63. Is that right? Maybe I screwed it up. Yeah, I'm sorry, I screwed it up because I got the wrong number. At the end, it wasn't 0.37. At the end, it was 0.36, so I misread the number. 0.36, so I need to fix this here. 0.36, fix that, sorry. And then this is 0.64, 64% reaction. Now it makes sense. Okay, so 2y is, and so this should be plus 0.64. And so at the end, I go 0 plus 0.64 gives me 0.64. And this is plus y, so this is plus 0.32. And so I go 0 plus 0.32 gives me 0.32. And so overall, what I see is I see 64% reaction. And why is that? Why don't I see 100% reaction? Because we predicted there's a driving force for this, right? But the thing is this. When we look at the driving force for this, what page was that on? That was A30. All right, so when we look at this, there is a driving force because copper 2 is a better oxidizer than tin 4. But how much better of an oxidizer is it? When you look at these are like, what would you say? Copper 2 is a significantly or, marginally. These are right next to each other. And so actually they're about the same in strength. If they're about the same, then what we have is like a little tug of war, and it's a more even tug of war. In Chem 1A, we had this type of reaction. We had no reaction, the reactants are stable. The products are totally unstable. There's a significant difference in the energies of those. And so there's no reaction, or we had 100% reaction, in which it was flipped the other way. And so, the further apart, that is, if one oxidizer is much, much stronger than the other, then there's a strong driving force. But if the two are about the same, you know what? Copper 2 is just slightly stronger, a hair stronger. If it's just a hair stronger, is this seesaw going to be so lopsided? No. What we're going to expect is, we're not going to expect this to all of a sudden go boom, The products are so much more stable. And we expect 100% reaction, all the limiting reagents gone. Over here, that driving force is less significant, and so it doesn't go boom like that. It goes, initially you start off like this, and then it goes boom, but it doesn't go. And so what we see is we see a mixture of reactants and products left over here. And so what that implies is that the delta G, yes, it's negative, but what would you guess the delta G is? Less than 25. Yeah, probably, it would be between, let's say, I would expect it to be between 0 and maybe 50, negative 50, and I'd expect it to be closer to 0. I'd expect it to be, maybe it's negative 8, just as a guess, negative 10. Just ballpark guessing. It's not going to be huge. And so what do we do when the driving force is not so big, one way or the other? When it's not so big one way or the other, then this is the type of stuff that happens. And we'll see this. Let's do some more experiments. So what we want to do now in Chem 1B is, okay, that's fine. We can deal with that. There's not a huge driving force, therefore not all of it reacts. Well, okay, now what I want to do is I want to do a prediction. And so let's do a new prediction here. My new prediction is going to be this here. We'll call it experiment 1. And so I'll predict this. Let's just make it. All right, this chart is the IE chart, not the ICE chart, the ICE chart, but I'm going to convert it into an ICE chart. So my prediction is, rather than starting with 1.00 molar, I'm going to start off with 0.100 moles. Not molar, moles. 0.100 moles, and 0 moles, and 0 moles. And my prediction is this. What did we predict? What was the percent reaction of the limiting reagent? 64% reaction? Is that right? And so I'm just going to predict 64% reaction. If I predict 64% reaction, I'm going to, if this is 100, I'd lose 0.064. That would be 64 out of 100. Or let's just move the decimal over. Let's predict 64% reaction, which is going to leave me with 0.036 mole at the end. And if we have 64% of the reaction of the limiting reagent, this is what we call minus 2y. Right? And therefore, this must be minus y. And so this is going to be minus y
y would be half of that, so it would be minus 0.032 moles, which would be our minus y. And so this would give me how much at the end? 0.068 moles. And so this must be here, this must be plus y, and this must be plus 2y, and this must be plus y here. So 2y is 0.064, so this is plus 0.064 moles. And so 0 plus 0.064 gives me 0.064 moles. And 0 plus 0.032 moles gives me 0.032 moles. Right? And so this is what we predict. Prediction based on 64% reaction. You got that? So we got our prediction based on 64% reaction. We go into the lab and observed. You know what was observed? 64% reaction. And so this is what this is showing here. The C part is missing. They just deleted that row. Basically, it started off with 0.100, 0.100. They end up with 0.036, 0.068, 0.064, 0.032, just what we predicted, based on 64% reaction. Now, let's go on to this one. We're going to go on to experiment 3, which is down here at the bottom. We go down to experiment 3 here. We're going to do the same thing. We put in 0.100, 0.100. But in this particular instance, what they did here was they threw in some products there. But if we throw in some products there, it shouldn't have any impact, right? Because we expect a 64% reaction of the limiting reactant. Okay, can you take a look at the values here and tell me, did we get it? 64% reaction. Okay, if we didn't get 64% reaction, what was the percent reaction that we got there? And can you set that up as an ICE table like I did with the minus 2y and the plus 2y's and predict? You know, what we want to do is we want to predict it. So first, ignore this. This is the experimental. And so ignore this for right now. Set up the ICE table and predict what we're going to get. That's as the final equilibrium or final end of a 64% reaction. Just have to do one thing. Okay, well, did you get it? You know, our predicted line here is one, it would be the same. We should get 0.034, correct? 0.034. Or 36, sorry, 0.036. We expect 60, this is our still a limiting reagent, so we expect 0.036. That wasn't observed. Here we would expect 0.068. Here we would have expected, well, we're starting off with 0.100, we're going to add some to it, so we're going to get 0.164. I would predict 0.164 here and 0.132 here. But were those observed? No, not at all. In fact, what was the percent reaction? If you look at the limiting reactant here,
What was the percent reaction? There. Well, we just moved the decimal 3 over, and it looks like 7.8% reaction. We only got 7.8% reaction. Why is that? 7.8%. I was expecting 64% reaction. 7.8% reaction. And so that was weird. And so what we're going to do is we're going to do one more experiment here. In this experiment, there should be no reaction, because if there's a driving force in the forward direction, there's no driving force in the reverse direction, right? It's spontaneous in the forward, non-spontaneous in the reverse, because delta G is negative. But when we look at this one here, we're going to start off with no reactants in all products. And so, yes, driving force forward, no driving force reverse, but look at what happens. What happens is, it doesn't stay like this. What happens is, some of it reacts. So we lose some products and form some reactants. That means the reverse reaction must have occurred. And the reverse reaction must have occurred because our limiting reagent here is copper again. And so if we look at the percent reaction in the reverse direction, just make that 100, we have 43.3% left over, which means we must have reacted 56.7%. So we had 56.7% of our limiting reactant react in the reverse direction. And so this is showing that, yes, delta G is negative, but delta G must be just a hair negative. And that's because, the strengths of the oxidizers on both sides are about the same. And so what we expect is we expect a two-way street. It's a very even tug-of-war between the products and the reactants in terms of the driving force. But the tricky thing here is, okay, if we expect it, it should be close to even. So it should be a 50-50 mix. Do we generate a 50-50 mix in all these scenarios? Does that look like a 50-50 mix to you? Maybe that's how we can predict it. Or maybe it's not a 50-50 mix because, the products are just slightly more stable. So maybe it's a 51-52% product, 49-48% reactant. Maybe it's that kind of mix. And so if we have this ratio, do you see it there? It's hard to see it there. And so in chemistry, what we try to do is we try to look for patterns. And one of the first pattern I looked for was percent reaction. I wanted it to be a pattern. I wanted 68% reaction each and every time I do this reaction, but it wasn't. And so what chemists often do is, you might not see the pattern there, so we might try to graph it. If we graph the data for experiments 1, 2, and 3, and then color code it, if we color code it, we might be able to see a pattern arise. In the first experiment, we had 0.1 moles of both reactants here. And we had 0 moles of both products here. And so the reactants reacted, which is the blue and the red, and the products formed, which is the black and the green. And so when I look at the ratio, yeah, it's kind of a mix, of reactant to product at the end. Do you see that? And so we have this pattern, blue, black, red, green, kind of tightly spaced like that. And then we go to experiment 2, in which we start off with just the products. We start off with the products. The products react, forming reactants. And so the reverse reaction occurs. When we look at the end pattern, take a look. Green, red, black, blue. Do they match? You see a pattern there? And then we go to the final experiment here, experiment 3, and do you see a pattern in the patterns? No, we don't. And so if there's no pattern in the patterns, maybe there's no way to predict this. Maybe, who knows? If you just flip the coin, that's your percentage reaction. But do you want to give up that easily? Now, sometimes finding these patterns isn't so easy. For example, if we go back to chapter 8, actually, I went the wrong way. If we go back to chapter 8, and look at the hydrogen atom spectrum. Oops. So slow for some reason. That's helium, sorry. Not helium, I want hydrogen. Do you remember the hydrogen atom spectrum? Can you visualize it in your mind? It looks like this. Red, green, blue, and violet lines. 4 lines in the visible spectrum of the hydrogen atom. Do you see a pattern in those lines? Can you see a pattern? There's a pattern in those lines, and that pattern was used to predict the lines in the ultraviolet and the lines in the infrared. And that pattern predicted the lines successfully. But the pattern is a mathematical pattern. And a mathematical pattern is, does the sequence of numbers fit a mathematical equation? And it turns out, yes, that sequence of numbers fits. This guy named Rydberg figured it out, and he came up with this equation. The energy of those lines is equal to minus r sub h, 1 over n final squared, minus 1 over n initial squared, where n final is 2, so this equation, r sub h is a constant, is 1/4 minus 1 over n squared, where n is greater than 2. It's an integer greater than 2. It's a mathematical pattern that fit the hydrogen atom spectrum. And so what we're going to do is we're going to do the same thing. We're going to look, is there a mathematical pattern Okay. Is there a mathematical pattern that fits these numbers here, or this graphical, when we graph it out, fits these? And so when you look at this, no, it doesn't seem like there is any, because the Rydberg, we have the red, the green, the blue, the violet, but this is all mixed up here. And so we don't quite give up, and we'll try to figure out a mathematical pattern. And so some of the mathematical patterns we try is take the ratio of the products to the reactants. Maybe it's a 50-50. We take the ratio of the products to the reactants, it doesn't come out 50-50 or anywhere between that. In fact, it comes out in bizarre numbers, which makes no sense, because it seems all random. To make a long story short, they tried lots of patterns, because that's part of the scientific method. The scientific method is you take your observations and then you look for the patterns. When they looked for the patterns, they tried lots of different forms of mathematical equations, like Rydberg did. And then eventually they came up with something that appeared to work.
And what appeared to work was a pattern that was observed in the equilibrium. The pattern that was observed to work in the equilibrium is this. Now, if I take the products, and what I do is you raise them to their respective coefficient. So 0.064 would be the copper 1. Copper 1 has a coefficient of 2, so we'll square that. And then the tin 4 is 0.032. It's to the first power. And so if you don't just take the ratio of products to reactants, but you take the ratio of the products to the reactants raised to the respective coefficients, then it seems to fit a pattern, because when we do this math here, it comes out to 1.49. That's for experiment 1. For experiment 2, do the same thing here with these numbers. And remember, the percent reaction was totally different. But if we look at the ratio of products to reactants raised to the respective power, it comes out to 1.48. Now, for experiment 3, do you see the patterns here? Comes out to 1.48. So it seems that, you know, no matter where we start, because if we do the same ratio with our initial state, you see the same ratio here is 0. That would be the initial state. The same ratio here is infinity. And the same ratio here. And so it seems to not matter where we start, but where we end is the most important. Where we end, it should have a ratio of 1.48. That's the mathematical pattern that we see. So it turns out there is a mathematical pattern. But there's one more complication. If I try to apply this mathematical pattern to other systems, it fails. And so I have to make one more modification to this. The one more modification is I can't use moles. I have to use molarity. Moles won't work. And so if I convert all these into molarities rather than moles, then it works. And we got a pattern. Okay, so I have to remember that. And so it did work with moles in this case, but this case is special. It doesn't work for moles in other cases, but it works for molarity in all cases. And so this is the pattern. And the pattern is called the equilibrium constant. And this number here is called K. K is the equilibrium constant for this. And so we have two things here. We have Q and K. What is Q? Q is your initial. The initial pattern. Remember, there's no real pattern here. Q, this is Q, is taking your initial concentrations and plugging it in, and it can be anything. It could be infinity, 0, 1, etc. But K, your final ratio, has to be this constant, which we call the equilibrium constant. And so here, we come up with the patterns. Q can be anything, but Q is just going to be your initial. So this would be the products, copper 2 raised to their coefficient, that would be squared. To make sure it's initial, we write an I there. Tin 4, initial, raised to the first. Copper 2 plus, initial, squared. Tin 2, initial. And so this is your Q. You can start off anywhere, but what happens is sometimes the Q is too big, sometimes the Q is too small. In this case, the Q is too small. You see, because the Q is 0, that ratio should be 1.49. So what this means is it has to grow. The only way this can grow is by adding product, decreasing reactant. By adding product, decreasing reactant, you can get it to go. And so this means forward reaction has to take place. But in experiment 2, Q is too big. Q is infinity. The correct ratio is 1.48. Actually, we'll average these three. 149, 149, 148. We'll call it 148.6. There's our correct ratio. And so this is way too big. That means we have to get rid of product and add more reactant. And so that means the reverse reaction takes place in the second experiment. In the third experiment, Q is too small. You know, it should be 148.6, it's 1, so we've got to grow. In other words, we have to make more product and decrease the reactants. And so Q is what we call the reaction quotient. The reaction quotient just tells us where we're starting. The equilibrium constant tells us where we have to end. And so K is where we have to end. K is going to be, it doesn't matter where we start, but we have to end here. And so this is going to be at equilibrium. We should hit 1.486, which is the average of those three. Just average them. I don't know which experiment was the best. The best thing to do is average it. And so if Q's too small, then we got to go forward. If Q's too big, we got to go backwards. It just tells us our balance. So let's say our balance is 1.48, which means we need a little bit more product than reactant, right? And so if Q is too small, that means the seesaw's tilted like this, we've got to go forward. If Q's too big, it's too left side, we got to go backwards. That's what we do in this equilibrium. And so, this gives us a way to predict, because based on this pattern, we should be able to predict something like this. So for example, if I have this, I'm going to go with 0.348 moles and 0.127 moles and 0 moles and 0 moles here. I want to predict the stoichiometry of this. And so, can I say, hey, I got 64% reaction? Is that going to work? Can I say, what's my limiting reagent here? Can you see? Tell me what my limiting reagent is. Actually, the limiting reagent is now going to be the tin 2. So can I say 64% reaction of my limiting? No. Can I say 9.8% reaction? No. I want to predict where I end up. But I know I can't end up here because, what is Q here? Q is 0 because it's product over reactants. Products are 0. Numerator is 0. Q is 0. It's too small. It's too small. I got to build up more product. So Q tells me I got to have forward reaction. I need more product there to balance things out because right now it's way too lopsided. Remember, it's supposed to be like this. I'm like this. I got 0 on the left right now. So I gotta go forward. And so Q just tells me, do I tilt forward or do I tilt reverse or do I have forward reaction or reverse reaction? I gotta go forward. And so I don't know the percentage. Since I don't know the percentage, I'm gonna call it X. And so this is gonna be minus 2X. But can I use moles? Does moles fit the pattern? Unfortunately, moles does not fit the pattern. It has to be moles per liter. So I'm gonna say I'm gonna dissolve that in 1 liter. And so that comes out. And so this is minus 2X molar. This is going to be minus X. I have no idea what the percentage is because the percentage is all over the place. Sometimes it's 64%, sometimes it's 9.8%, sometimes it's something else. But that's okay. So we'll just say plus 2X here, plus X here. We can say this, no problem. And so at the end, we just figure it's going to be 0.348 minus however much reacted, which is going to be 2X. So it's going to be 0.348 minus 2X molar. This is going to be 0.127 minus X molar. This is going to be 0 plus 2X, which gives me 2X molar. This is going to be 0 plus X, which just gives me X molar. And I know that these have to be the equilibrium concentrations. So this is going to be the equilibrium concentration of copper 2. This is going to equal the equilibrium concentration of tin 2. This is the equilibrium concentration of copper 1, R. And this will be the equilibrium concentration of tin 4. Well, I know that the ratio of the equilibrium concentrations has to equal 1.486. But, this is 4 unknowns here. About 4 unknowns, I got multiple equations that I'll have to use. I'll have to do some kind of multiple unknown, multiple equation type deal. But you know what? What I can do here is this substitution. Rather than leave it as this, I know that it's going to be equal to this expression here. And these will be equal to this expression here. And so what I'll do is I'll take this 2x and plug it in here. So this is going to be 2x, and then I have to square that concentration. And this is going to be x, which I've raised to the first power. And then this is going to be divided by this, 0.348 minus 2x. It's going to be raised to the second power. And this is going to be 0.127 minus x raised to the first power. And so when I look at that, then I go, hey, now I have it only in terms of one unknown. There's only one unknown here. So I went from having 4 unknowns to 1 unknown. Now can I solve for x? Yeah. And so I'm going to solve this for x. Actually, not me. I'm going to have you solve it for x. We have about, how much time do we have left? 3 minutes? How long do you think this would take you to solve for x? You know, this is just algebra. Right? Just algebra. How long would it take you to solve for x? 3 minutes? 10 minutes? 30 minutes? 1 hour? Never? You know, I've given problems like this on the test, and some people never finish it. Even if they stay for 1 hour working on this, they can't do the math. This is hard algebra. Right? This is hard algebra, but if you have a calculator, well, what calculator you use? Well, probably the most powerful calculator that you're allowed to use for standardized tests is the one I recommended, the Casio. Did anybody buy that? The FX115? You got it? And so what you could do is, with that calculator, you can get this into the form. You know, you get it into the ax cubed plus bx squared plus cx plus d form is equal to 0. And with the Casio FX115, you can plug in A, B, C, and D, and then it'll spit out. But, you know, that's as powerful as it gets. The most powerful as it gets is to solve a third order or cubic equation. If you have a fourth order or a fifth order equation, unfortunately the Casio won't solve that. And do we see fourth order and fifth order and sixth order? Yes, we do. And so is a Casio FX115 required, mandatory? No, it isn't. And so how are you going to solve this without using a calculator? Well, you got to use a calculator, but how can you solve it using the cheapo calculator? That looks like the TI-30XA. TI-30XA is the cheapo calculator. It can't do anything like this, but can you solve this? And how would you solve it? Yeah, you could solve it. How would you solve it? Well, maybe I'll just try to simplify it. You know, 2x squared, it's going to be 4x cubed over 0.348 minus 2x, quantity squared, 0.127 minus x. Is equal to 1.486.
The 0.127 minus x be squared too?
No.
No.
It's raised to the coefficient.
Okay.
This is the pattern. Don't ask me why. It's just a mathematical pattern that seems to work. And so we could call it a law. And it is a law. This empirical equation is the equilibrium law. Okay. And because it holds for lots and lots of equations. So that's why we call it a law rather than a rule or something like that, or just a plain old observation. Well, have you ever tackled a problem like this? And is it easy or is it hard, or how do you solve it? The guess and check, right? You might have done this in Chem 1A with the, what was that equation? Van der Waals, you're right. Eric remembers because I gave this problem in Chem 1A. I gave a problem where it's a higher order. It was v to the minus 2. The Van der Waals equation, when you solve that for volume, it becomes a guess and check. But guess and check gets a fancy name in Chem 1A. What's the, do you recall the fancy name that we give it in Chem 1A?
We don't call it the guess and check. Guess and check they use in elementary schools. So we want a more sophisticated name for the guess and check method. Yes, method of successive approximations. And where can you find it in our book? Well, you find it in appendix. It's appendix A6. And unfortunately, we have to use this method a lot because we get hit by these. We get hit by things like this, fifth order equation, sixth order equation. There's no way you're going to solve that by grinding out the math. And so you'll have to use this. Are we out of time here?
Yeah.
Oh, sorry. What time do we end?
2:25.
Okay.